Hey, excited to be here in Belgium. Today we're talking about protecting the world's greatest open source ecosystem with Java. With Sigstore. The ecosystem is Java. So this is us. I'm Appu, on the bottom right. I'm a software engineer at Google. I've been working in Java tooling for a while. I worked on Jib. That's pretty, if you've ever used that. I also maintain some distroless images, and I'm working on Sigstore.
And I'm Patrick Flynn. I live in Montreal. I work at ChainGuard. I've been working on the ChainGuard Wolfie undistribution, ChainGuard images, and sigstore-java.
Let's keep going. So why should you care about software supply chain security? As you can see from this very exciting graph, very executive-friendly graph that's up and to the right, software hacker profits are at an all-time high. Attackers have been finding new ways to attack software, not while it's running anymore, but before it even starts running, at the source, during build, and even during distribution. So what can we do? We're here to talk about Sigstore. So that's what we're trying to do. We think Sigstore can help solve some of these problems. So what is Sigstore? It's a fast-growing open source community. It's several projects within the OpenSSF, which is part of the Linux Foundation. It contains free community-operated and publicly available services like a transparency log and a certificate authority, and a bunch of language clients to simplify signing and verification. It's modular and interoperable with existing PKI and auth standards. We're not inventing new crypto standards. We're just trying to make everything easier to use. If you remember Let's Encrypt, when it started, it helped secure communication all over the web by making it easier and free to obtain certificates. We want to do the same for software signing. Make it free, easy, and ubiquitous. See you.
Yeah, so many of you, I imagine, probably have never heard of Sigstore, so it probably makes sense to focus a little bit on why Sigstore exists. Ultimately, what problem, is it solving for you? Ultimately, really what we're trying to help you understand is whether you can trust your dependency tree. You need a way to be able to determine whether the binary that you're including in your application is actually coming from who it claims to be coming from. The attacks are real. This is happening more and more, as you saw in that graph. There are various ways in which your dependencies can become compromised. It starts at the source, right? If somebody gets access to your GitHub credentials and can actually get code into your repo, you're kind of hosed, right? They can get, if you're using CI for the signing and automated pushes to the repos, their hack is going to look completely valid to your users. Another form of compromise is if you're using PGP and you get your private key stolen, that's not good. And that means that an attacker can forge your signature and make their compromised version of the dependency you're using seem like it's the right one. They can obviously, if you don't have 2FA enabled for your package manager and you happen to be an open source maintainer, it's pretty common to get your credentials hijacked these days. If somebody gets access to those, and this has happened also, they can push whatever kind of artifacts they want to your namespace in the package repository and reach a lot of users that way. There are also dependency confusion attacks, which is effectively because in enterprise sometimes you'll have internal repos and there'll be fallback algorithms, or even on Android for a long time with Gradle, people would have JCenter and Maven Central configured as repositories in their builds. it would be the case that, and this happened and compromised millions of Android phones, somebody, like some popular open source package was not registered on JCenter. So an attacker basically took over that namespace and was able to distribute and own like quite a lot of devices. Finally, you've got typo squatting, which is kind of like a spray and pray approach to attacking people, because you're just kind of hoping that somebody's gonna, make a mistake when they're typing in the namespace and pull your version instead of theirs, instead of the right one. But it's happened, and it actually happens quite a lot. And you can reach quite a lot of devices that way too. And so what are the solutions? Like the chain guard approach to much of those problems is trying to imbue cryptographic trust throughout the supply chain. And most people know about cryptography being a valuable thing for sort of hiding secrets, for transmitting your credit card to Amazon when you're buying whatever it is you buy. But it also can be a form, and it really importantly is a form of verifying identity. So don't worry, today I'm not going to talk about like modular exponentiation or discrete logarithm problem, but it is important to realize that digital signatures basically are the basis of everything that's enabled commerce and privacy online, and it's done so for decades. Ultimately, if you sign something, you are proving to an entity that you are the owner of the private key peer to the public key you signed with. And that's generally useful, right? And it's not new. As you know, probably if you use Maven Central, or maybe not, even though you use Maven Central, every artifact in Maven Central requires a PGP signature. And websites obviously use this very effectively today. So why aren't we signing all our artifacts? Like I said, Maven Central enforces PGP, so there are signing there. But the reality is that, like in other ecosystems, people just don't sign, or the systems make it optional. And even if you do sign, with PGP at least, Jason Van Zyl, a co-founder of Maven and Maven Central, points out here that only around 2% of folks that are downloading artifacts are also downloading the signatures that go with them to verify them. So signing is great, but if you're not verifying, there's not a whole lot of value there. So what's going on, right? Why are you not signing? And for Java in particular, why isn't anybody verifying these binaries? And the answer is really simple. It's because developers are lazy. Yeah, well, not everybody, but most people. We have like 2% of developers who aren't lazy. I'm only half joking. The reality is that developers don't go through, or are not willing to go through a lot of toil to get value. And ultimately, managing your own keys involves a huge amount of toil. So speaking of which, right, if you're using PGP, imagine a typical application you're deploying to production, a Java application, your transitive depth tree is probably exposed to a significant amount. Like you're talking about hundreds of jars sometimes. And that means hundreds of open source maintainers. Some of them are coming from like enterprise areas where everything's signed and going through CI. Some are being built on somebody's computer, and that hobbyist is not going to go through the trouble of storing their PGP key somewhere safe, somewhere where they can reliably get access to it, and then somewhere where they'll know if it's been accessed. What happens when those folks lose their keys for good, or when their key gets compromised? The other problem is key distribution. So I don't know if you're familiar, like for verification to actually make sense in the PGP world, it depends on the web of trust. And one of the sort of ceremonies in the web of trust was like the idea of a signing party. Everybody gets together with their PGP keys, they sign each other's keys, And over time, hopefully, you have like a transitive connection between somebody you really know with the public key that you trust, that you've seen in the real world, to the public key that you want to verify. This is a great idea, but in practice, at our scale, in the global world, it doesn't really work. And I believe Hervé is going to talk about this in a talk right after this one, so I encourage you to go check out his PGP versus Sigstore talk for Maven Central. The CA authority model, the one that you see used in the web, has proven to be pretty successful, and Sigstore has taken that approach instead. So how does the CA authority model work, right? Like ultimately, what problem is it solving? So we have Appu here, and Jason Van Ziel, another contributor to sigstore-java, who's worked on the Maven plugin. Now they're separated by the metaverse. Appu has never met Jason in real life. They need to talk. They need to trust each other's identity, which means that Appu needs to trust Jason's public key, but he can't just take it from Jason. It just doesn't, there's no reason for him to trust that public key, because there could easily be a man-in-the-middle attack where the public key is replaced by some other public key. So Appu needs a way to actually determine that that key is safe. An easy way to sort of look at an example where that problem is solved is online, right, on the web. If you take a look at this browser window, I'm sure you've all seen this, and you look for this when you're doing online transactions or want to preserve your privacy. It's that lock icon up in the browser telling you that your communication is going over HTTPS. HTTPS makes use of certificates, and those certificates are actually coming from the same server that is serving the google.com, right? That certificate includes a public key, but why are you trusting it? The answer is the certificate authority. The certificate authority solves this problem by creating a trusted third party that is not just somebody on your web of trust. It's like a large business with an office and people, and they go through the hard work of verifying that the public key that wants to assert that it is some identity is actually belongs to that identity. Of course, it has its own bootstrapping problem, right? Why do you trust a certificate authority if you've never been there, if they've never given you their public key on a piece of paper or something? And the way that's solved, and it's not perfect, is that at the moment, typically CAs have their public keys baked into your operating system, right? So many of you might know this. Like you can find a list of the CA public keys in your OS. Browser vendors have also started, and it's been a while, baking CA authority public keys that they trust into the browser. You can still be compromised, right? If you download and don't verify some Linux ISO, or if you get owned and your actual database of public keys gets changed. And those kinds of attacks have happened as well. So how can Sigstore replicate this model of having a CA-based authority to verify everybody's public keys, right? That's a lot to handle. We need to safely generate the keys for the root. So we need these private keys. We need to store those keys somewhere safe. We need to be able to handle rotation, and we need somehow to handle distribution as well. Tough is the framework that we use. It was developed, I think, as part of the CNCF, and it's used by a number of large companies whose name generally kind of all are missing from my brain at the moment. They provide a framework for distributing really important things like software updates and keys. So one of the really key parts is that you want to be able to suffer the compromise of a key without being completely owned. And one of the ways we do that at Sigstore is instead of having one private key for the root, we have 5. And those 5 keys are owned by 5 separate people, distributed globally, and stored offline in secure hardware. This means that if 1 or 2 of those keys gets compromised, we can still push forward. Tough also helps us protect against malicious mirrors, rollback attacks, fast-forward attacks, and many more. So now that we have a safe public key and private key pair for our CA root, how do we distribute them? We actually distribute them with our clients. So if you're familiar with Cosign, the CLI, or if you use sigstore-java, the CA root public keys are bundled with the clients and then copied into your system at initialization time. So behold, we have a new code signing CA, and its name is sigstore. That's pretty amazing in itself. So why is Pedro crying? The answer to that is, I don't know if any of you have ever obtained an HTTPS certificate before 2014. Raise your hand. If you thought that was a fun experience, keep your hand up. Yeah, so getting a new HTTPS cert back in the day was sort of like applying for your driver's license. It was something that you had to do, maybe you called somebody up, or you had to submit photo ID, you had to pay money, and it took sometimes weeks to do. And clearly nobody wants to do this for most especially nonprofit use cases. Ultimately, this made HTTPS certificates inaccessible, right? It's more another example of developers being lazy. They're not going to go through that experience to get to HTTPS. And ultimately, it made the web less private and less safe. But something seems to have happened, right? If you look at this data from Google from 2016 to 2021, we see that the amount of basically the HTTPS percentage of the internet has gone from around 40% to close to 90%. Does anybody here know why? Thank you very much. That's exactly why. Let's Encrypt made getting an HTTPS certificate easy enough that even a developer would do it. Not only is it easy now to get a cert, you can automate it. And we have these great tools like CertBot and Cert Manager on Kubernetes that handle rotation and everything for you. Suddenly, you don't even need to know about how to handle certs. It just gets done right. And this is really evidence that developer experience matters, and it's the lesson that Sigstore thinks it's going to successfully apply to code signing. We can't get developers signing and verifying code without a fantastic developer experience.
Yeah, so let's talk about Sigstore's keyless signing. So a little meme here, it says we don't need keys. We still use keys, but we're trying to remove the burden of signing and we're trying to remove the burden of managing keys from signing. So let's solve some problems with Sigstore that we mentioned earlier. We want to prove who signed something. We want to know how to store our keys, and we want to know how to monitor and audit signing events so we can detect maybe a loss of a key or identity or something. Let's start with Fulcio. Fulcio is one of the infrastructure services that Sigstore provides. It embeds your verified identity in the certificate. Unlike PGP, where you could just say, hey, I'm, CEO of Microsoft at Microsoft.com. Fulcio will verify that you do indeed control that email address. We use short-lived signing certificates. This helps it keeps you from having to manage keys. And we discard private keys after use. Every signing event, you just talk to Fulcio again and accept and obtain a new certificate. Since it's a CA, it also comes with auditable transparency logs. This exists Right now, for all CAs, Chrome will check against transparency logs when it verifies a certificate. So let's try to answer the question of who signed this. OIDC tokens are a way to show identity. They're issued by various authorities for people or even machines. So in this case, we have an OIDC provider. You may have seen something like sign in at Google or sign in with Google for some third-party site. They obtain an OIDC token that proves your identity. So you can sign in, like say I'm a human at test.com, and this information is embedded in the OIDC token so someone can use that to verify your identity. Similarly, infrastructure providers can provide identity information for machines or workloads. GitHub Actions does this. It has a workload identity, and you can attest to something happening as part of an action within the GitHub infrastructure. Now, we're not actually saying you have to pick proving that you're a human or a robot. It's up to the release engineer and process to decide whether to include humans or trust in the machines. No Skynet, please. But the Sigstore's goal is to provide the mechanisms to use the identities to fulfill like anyone's security requirements. To continue on who signed this, when you're asking Fulcio for certificate, you have to prove that you have the private key along with the public key. So one simple way to do this is to just sign the identity and send that signed identity over to Fulcio along with the token and the public key. Fulcio can then decode the signature using the public key and decide like, hey, yeah, you probably have the private key. So what's going on here? We're essentially trading proof of our identity for a code signing certificate. And this fine gentleman is the Fulcio computer, and I'll send him away. So let's go through the whole process of obtaining a signing certificate from Fulcio. You first obtain proof of identity, so that can come from your OIDC provider. You generate public-private key pair, use the private key to sign the identity, and then you send the token, signed identity, and public key over to Fulcio. Fulcio does some verification here. It verifies the ID against the OIDC provider. So it says, you claim to be Appu at google.com. I'm going to go ask Google to make sure that that's true. It verifies that the public key is the one that you're signing with, or is the companion of the private key that you're signing with by checking the signed identity, and then it issues you the certificate. So in this certificate, you can see there's the public key, and then there's a bunch of information that Fulcio adds in. There's the subject, or the identity that we are claiming. There's the issuer, who's the authority that is attesting to that identity. So if you're writing policy on this, you can say, hey, I trust Facebook.com, but I don't trust bake.com. That's not a trustable OIDC provider, even if they claim to have like your username. It has a short validity period. This helps us with like avoiding revocation and storing of keys and stuff. And it has the reference to the root, which is Fulcio. That is actually also distributed with Tough. So when you're doing verification, you can verify up to the root. Where do I store my keys? So we're not actually storing any keys in keyless signing. We use ephemeral keys. We don't care about long-term private key storage. So we put the public key in the signing certificate. If someone wants to find that, they just need the certificate. The private key we use to sign our artifact. We obtain a signature, and then we throw it in the trash. So instead of keeping track of your private key, which is a bunch of random strings, you now keep track of your email password, which may also be a bunch of random strings, but you're much better at protecting this. So let's go on to auditability. Recore is the Sigstore transparency log. It's a trillion-based transparency log, which uses a Merkle tree. Merkle trees are the basis for Git and certificate transparency. The feature of this log is that it's append only with an immutable history. We use Recore for two things in keyless signing. We register the signing time with the transparency log. Because we have short-lived certificates, by the time you do verification, the certificate probably is expired. So you need something to tell you that signing happened during the validity period. So Recore kind of gives you a timestamp and says, hey, yeah, looks like a signing event happened in that 10 minutes that things were valid. And Recore is open and allows third parties to monitor and audit signing events. And this is helpful to kind of maintain the integrity of the log. Like, not only do you have to trust Recore, you don't just have to trust Recore. You can say, hey, all these third parties have checked the integrity of the log, and it seems to be consistent. And there is a possibility that you can provide services to users. Like, you can say, hey, these are all the signing events you did. Are all of these you? There was a new one, but it came from hackercountry.com. Maybe you should go look into your identity and take some actions. So what do you upload to Recore to put in the log? We don't upload artifacts. We only upload the digest. This is because Recore is not storage for your artifacts. You do not go to Recore to download artifacts. You go to your package repository or your release bucket or whatever. Recore only stores metadata, so it stores the artifact digest, the signature, and the signing certificate, which contains your public key and all this other identity information. So you send it over to Recore. Recore verifies the signature, and then it signs and enters it into the log. This log entry is important because it contains the timestamp where it kind of observed the signing event. Recore also signs all this information, so if you ever get this log entry from an alternate source, maybe it's stored offline, instead of asking Recore for it every time, you can just check that the log entry was signed using Recore's private key. Recore's public key, again, is distributed with TUF. So what do you, as a library or binary developer, distribute? You distribute your artifact. We can use that to calculate the digest if we need it. And then the signature and the signing certificate. You can also distribute the log entry, which contains the timestamp, or you can ask Recore for it every time, which can be expensive, both to the verifier. Say Maven Central is accepting thousands of requests. You don't want to have to hit Recore every time. But the entry is important because it has the timestamp. So you need to store all these files. It's a lot of files to add to your Maven release. We already have a lot of files. We have sources and Java doc and POM, and we're trying to put this all together in one single metadata file, but that's not quite ready yet. So let's just keep going. So how do you actually audit and monitor? Since the Merkle tree is open, you can take your binoculars and look at it like this man here. There are currently only two kind of working monitors. There's one from Purdue University and one from Trust Fabric. The space isn't fully explored. Sigstore is always accepting contributors. So if this is a space that's interesting to you, we'd love to have you. We'd also love to have you work on sigstore-java. This is a Java conference with Java experts. So let's move on from there. So that's a lot of things. Do I have to do this every time I sign? My head is going to explode. And the answer is no, because we have clients. And the clients will orchestrate the keyless signing workflow for you. And they integrate into the tooling you know and use every day. So there's clients in Go, Rust, JavaScript, Python, and there's the sigstore-java client, which Patrick and I work on. This is the best one. Let's give it a trophy. And sigstore-java is an official Sigstore project within the Sigstore repository. We did a early release, 0.1.0 is our first release on September 1st. You can see the code there. It's a native Java client. You don't have to use someone's Go binary to integrate into your Java tooling. It's general purpose. We're trying to make it so that all the components you can swap in and out, and you can build your tooling around it. We're working on clients for Maven and Gradle, and it has full keyless signing and verification workflows. So it's demo time. Which one of these is? Okay, so am I here? Why won't the mouse? Oh, there we go. So let's have an artifact. And we're going to assign this artifact. It says hello, and we'll just add devox Belgium 2022. Does anyone have a favorite word? Banana. So that's just a simple text file. And in here, I have an example of signing. Which one is this? Sign. So here we're making use of the sigstore library. Why is this open twice? Oh, sorry. So we're just importing the sigstore-java library and O.10 from Maven Central. And I have a simple program. It's a main that accepts one parameter, the artifact. And we have this keyless signer object. So this comes from the sigstore library. It's a builder, and we have sigstore public defaults. So there's sigstore public infrastructure, which includes a full CO instance and a recore instance. And these defaults are kind of baked into the library to make it easier to use. But if you want to, you can set the client. You can set the OIDC client. So this is something that, to verify identity. You can set the signing mechanism. I think right now we just use ECDSA as the default. You can set the recore client. You can always use sigstore staging default, which is our pre-release infrastructure. We mostly use it for testing and verifying that clients will continue to work during upgrades. We're going to assign the artifact into this result object. And then we're going to save the results down to the disk. So the result object contains the digest that it's signed, certificate path, which is like all the certs in the chain, the signature that was generated, and the recore entry that was received when we tried to put the entry in the log. So let's run this. I have a little script here that just runs this program with this parameter, that artifact that we built. So let's run sign.sh. It's going to bring up a browser window so I can log in. This is actually the DEX OIDC provider that's part of Sigstore, and it's just a proxy to these three options. You can log in with GitHub, Google, or Microsoft. I don't have a Microsoft account available on this browser, so let's log in with Google. It's kind of, so I'm already logged in, so it kind of bypasses all the whole login flow. And if we look at the artifact directory, we now have a bundle, which is the recore log information. We have a certificate, and we have a signature. So what's in the certificate? Let's make sure, right. So this is all just base64 encoded. We can use OpenSSL X509 to decode this and show us everything that's going on here. Okay, so here's the full certificate. We can see that it was provided to us by Sigstore. Here is the validity period. It says 303 to 313. don't know. Oh, it's GMT. Okay, so we're 2 hours ahead. And one more thing. The identity. So here's my email, appu@google.com, and here is the OIDC provider, so accounts.google.com. If this was like accounts.goggle.com, you probably shouldn't trust it. And then there's a bunch of like standard certificate information, including my public keys in here somewhere. So it's over here. Okay, so that's the certificate. Let's look at the bundle that was returned. So this is just a bunch of nonsense. Let's pipe it through JQ. The bundle contains the base 64 encoded digest, certificate, and sign signature, and then a bunch of like log information. But what's important to us right now is the integrated time. So this is the timestamp we're using to verify that signing event indeed was registered during the validity period of the certificate. So JQ-R. So let's extract that out. We'll decode. Oh, that's not what I want to do. Sorry. We'll integrated time. So here's the time. Integrated time. All right, that's just like some long. So let's try and convert that into something we can read. So it says 3:03 with 19 seconds. And if we scroll back up to the validity period, it's 3:03 and 18 seconds to 3:13. So we can kind of say, yeah, it's during the validity period, so great. If we want to like take a look into the bundle to look at the content, let's extract the body out. Let's pipe it through base 64 because it's base 64 encoded, and then pipe it back into JQ to read it. So here's what's in the body. It's a hash record type, which is a type of entry into the log. And here's the hash of the artifact. Here's the signature, and then here's the public key certificate. We can kind of look at this hash and check if our artifact is truly that hash. So it's EOE 72 something something something. Let's do a SHA-256 sum against the artifact. And you can see it's EOE 725 so and so and so. Hopefully that matches. Pretty sure it does, but also hopefully it does. So we can then now we have all this information and we can verify it, but let's try and verify it without using sigstore tooling and instead use tooling that exists today. So to verify using OpenSSL, we have to extract the public key from the certificate. So let's say certificate, and then let's just put it in something called pubkey.pem. So this is just some simple public key. And then let's use OpenSSL now to verify. There's the public key, and then the signature is signature, and then the artifact that we want to verify the signature of. So here it says verified OK, which is not a lot of information, but that's all it gives us. And we can try and make sure this still works. Let's put bananas and check the verification. It says verification failure because it's not a signature for that artifact. Let's go back, make sure it still works. Okay. So cool. So that's generating the signature, and we're using existing tooling to verify it, so we know that we're doing things that already exist today. Now, if we keep going, we can try to use the library to verify the signature and stuff. So here I have another simple program that takes in 3 arguments: the artifact, the signature, and the certificate. It converts the artifact into a digest over here, and then it uses the keyless verifier, which is similar to the keyless signer object, against public sigstore. And then here we have a simple call to verify online. Verify online is a verification that requests the bundle from Recore instead of relying on the one on the disk. So this accepts a digest, a cert path, and a signature. And if it works, it'll print verified. If it does not work, it'll print stack trace. So in here, again, I have like a little script because it's hard to type all this. It's the artifact, the signature, and the certificate. Verify. And similar to OpenSSL, it just says verified. If we want to like go mess with the artifact again, we can try verifying, and it'll print keyless verification. So it says Recore entry not found because it locally generates the Recore entry and then tries to find it on the log and then obtain all the information it needs. We could probably do a better job with the messaging there. So this is just the raw library, but this is not what you're going to be using every day. You want to use Maven or Gradle or whatever you're using. So let's go to the Maven demo. So in this demo, we have a simple Maven program that doesn't do anything. And you'll see here I have this alt deployment repository. This is just a local directory, so when I do Maven deploy, I can show up locally instead of having to go to so1.oss.sonatype.org and log in, and who knows. Here I'm using a snapshot because I made one slight modification for the demo, but this should work as normal. I'm ignoring PGP signatures because this laptop is new, and I don't have any PGP signatures on here, and the agent's not set up, and I ran into a lot of issues. So this app doesn't do anything. It says hello world devox. We can add a banana in here. And it should just work with your standard Maven. We're injecting sigstore sign in between package and deploy. And what this is going to do is build the application, sign it with sigstore, and then deploy it to our local repository. So here we're logging in again. I'll log in with GitHub this time so we can see what the certificate looks like there. Oh no. Okay, so it's all done. It's all in there. Let's go check that local repository that I have. It's called repo. So there's a bunch of files in here. And you can see here the jar, there's all the required hashes, but there's also this PEM file, and why doesn't escape work? There's a PEM file right here, and then there's a SIG file, which is a signature. So let's go take a look at the PEM file with OpenSSL again. And here you can see, just for example, that the OAuth provider is now GitHub. Okay, I think we're running low on time, so let's just go back to the presentation. Hopefully that demo made sense.
Yeah, so sigstore is more than just a bunch of code. It's really become a pretty significant community.
What happened?
Oh dear. Okay, here we go. Oh. Do you know how to bring that notes back on?
Yeah.
I'll just talk to it. Yeah, the sigstore is basically
Sorry.
is the founding member of or one of the founding members of the OpenSSF project. It's I don't know if you've heard of the OpenSSF, but it's an organization dedicated to software security in open source. Yeah, it's one of the top 25 Linux Foundation projects, and we've only been around for a couple of years, so that's pretty impressive. It's got 1,400 members on Slack. We have regular community meetings with maintainers of various ecosystems, including Python, Ruby, Node, Java. It does include a bunch of projects like the Cosine CLI, Sigstore, like various client libraries, as well as infrastructure repos for actually operating the services, which brings us to kind of a unique aspect of Sigstore that we actually operate a bunch of production services. It's kind of similar to a package manager, but we do it kind of in a consortium of members of the OpenSSF. So we have Google, GitHub, and ChainGuard all collaborating together, donating people and money to operate and make sure that sigstore.dev is a reliable service for all of you. Targets is actually 2.5 nines. GitOps based. The log monitors we don't operate, but that's better, right? You don't want the verifiers to be us. We have seen quite a lot of adoption already. Notably, Kubernetes is already Sigstore signing and verifying all of the containers that make up their deployments. Python, the runtime, is also Sigstore signed. NPM, GitHub, Maven have all announced that they're adopting Sigstore, so it looks like it's really happening. It's a very exciting time. And there are vendors now that are making sort of Sigstore as a service a reality. A lot of enterprises are not going to want to necessarily be signing on our public Recor logs, for instance, or using our public Fulcio. And vendors are going to make it easy as possible so that you can use Sigstore on-prem or in the cloud, but not in the public. What we're working on, well, there's about 2 minutes, okay. What we're working on a GA. That's going to be announced really soon. At that point, we'll have 24/7 on-call, and we will be, I think we're already meeting our SLA. A better signature bundle, you saw in the examples that there were multiple files, and that there's kind of a babushka doll of a base 64 in there, and we're improving that significantly. We're going to have one signature bundle, and it's going to enable offline verification as well, using the tough roots that are bundled with the client. Sigstore tough client isn't complete, so working on that. sigstore-java, Maven, and Gradle, getting those to 1.0 are big priorities for us. Maven Central, adopting Sigstore, is also a huge priority for us. They've announced that they're going to do it. Ultimately, I think it's up to us to make it work for them first. And provenance generators, which, if you're curious about provenance, I highly encourage you to check out the SALSA or SLSA project. It's also part of OpenSSF. Join us if you're into making Java a safe ecosystem to use, especially making open source viable. I know it's already viable, but it needs to be safe, and all these compromises are kind of challenging the open source community and the adoption of open source. Sigstore.dev is a great website where you can find out about us. GitHub.com/Sigstore is where we do all our work. You can find all our projects there. You can, if you go to github.com/Sigstore/community, you can find a Slack invite to become part of our Slack community. These are my and Appu's Twitter handles, and thank you very much for coming. And it looks like we're out of time.